Okay.
Afternoon, everyone. Whether am I audible?
Yes, sir.
Yes, sir.
Okay. So this is a new mode of teaching. That's why you have to cooperate with me so that we can complete that class smoothly. Now, one thing I have done before starting this class, that is, I have stopped sharing my portion of the video just to take care of some bandwidth so that I can take other classes as well. Fine. And right now, all are audible to me. I have unmute all. Fine. So once you are asking or having some query, please one by one try to do that. That would be better. So class must be interactive. Fine. So I'm doing one thing that at first I can hear you all. So make it an interactive session so that it will be helpful for me to understand that any kind of difficulties you are having or not. Fine. So this class actually is the continuation of the last class, although we did that most probably before the midterm exam, most probably. That class was based on that counting technique. So today's class is also a continuation of that counting technique. As I mentioned on that day, that this counting technique, uh, some of the things we know already, like combination, permutation kind of thing. So our intention, objective of today's class is that we could just revisit those things and we try to nurture those known things today. Along with that, permutation combinations, few new techniques of countings are there. So one by one, we'll try to cover that one. So I'm starting the class with a topic that is a pigeonhole principle. So as I mentioned to you that what are the counting techniques actually we follow uh, during this time, like permutation, combination, and before these different counting technique, I mentioned that we have to select one basic counting approach at first. What is that? That is sum of a rule of sum. That is a counting approach, and rule of product. So rule of sum and rule of product, if you remember, that time we mentioned where we can apply rule of sum. Now, if we are counting and those counting, it is independent. That means they have no dependency. So object 1, n1 is the count, object 2, n2 is the count. If this way, object 1 and object 2 counting are not dependent, we say that rule of sum is required, and n1 plus n2 is the total number of way we can count either object 1 or object 2. That is rule of sum we mentioned. And rule of product, clearly a term is comes that time, that is dependency. So if it happens that you have to complete the count of first object and then only you can go for the second object count, then this way dependency comes, and that time rule of product comes. So that's why in that case the total number of ways we can count object 1 and object 2 becomes n1 into n2. And that is the approach we know that in case of permutation we get how n factorial comes. Now first we choose one object how many ways, n ways, then the next object how many ways, n minus 1 ways. So that's why factorial goes this way, n into n minus 1. That's a rule of product, we know that. So these basic approaches as well as permutation basic concepts as well as combination basic concepts we know. And regarding permutation, as we know that ordered data is required. So that's why a rule of dependency as well as ordered. This way we are trying to relate them. And combination, there, which one is unordered counting? Unordered counting. Now, if that basic approaches are clear to us, then quickly go with this new technique of Phrygian hole principle. Actually, the rule is very simple. The rule is saying something like this: pigeons are there and their nest by hole somewhere it is placed. Now one by one pigeons are coming and they are going inside the nest by hole. Now if this way it is kept somewhere, then it is saying that n number of pigeons and k number of holes, n number of pigeons and k number of holes, suppose it is there. So that's why if I go this way, if k plus 1 objects are assigned to k places, so k plus 1 actually object means it is talking about pigeons. So k plus 1 number of pigeons are assigned to go inside k number of nest by hole. If this way it happens, so clearly it is indicating that then at least one place must be assigned more than two pigeon by objects must be there. So if we consider this way, that k places individually we have placed this k number of objects. So one remaining, where that one will go out of this k number of hole, anywhere it will go. And if it goes that way, this extra one, it goes into that particular place. What will happen? That particular place, a certain place, it will have more than one object. So that's why it is mentioned here more than one, that is two. So pigeonhole principle is this, that it is ensuring at least one hole but nest will be there which is having more than two. At least, make it clear, at least we have mentioned. Why? Because it may happen that some holes are there which is having more than two, more than three, more than four, quite possible. So at least one hole, it is ensuring that more than two must be there. How it is ensuring that? Now this one plus one, that is ensuring that. So exactly, whether this is a counting technique or not, if we have to understand that particular approach, then uh, wait a minute. '25, like this one. So based on pigeonhole principle, we are having one problem. Problem is saying what is the minimum number of students required in a discrete mathematics class to be sure that at least 6 will receive the same grade. At least 6 will receive the same grade. If there are 5 possible grades, A, B, C, D, E, D, and F are there. Fine. So make it clear that whether it's a counting technique, yes, it's a counting technique, and a condition is coming. Which one is the condition? Now, at least we have to count in such a way, at least 6 will receive the same grade. That's the condition is coming. So actually, which one is whole and which one is Pigeon kind of concepts we can apply here. Now, these are the grades. That means these are the holes if we consider. Then which one is Pigeon? Now, Pigeon means student, number of student, how many pigeons are possible, so that this condition it will be fulfilled. So if we assume that individually 5 student I'm having and all are having different gate, so this way, this set of data if we repeat, that is next set of 5 students, they are also having individual grades, next set of 5 this way. So how many times if we go, so that we can ensure that 5 will get same grade. So clearly this is 5 into 5, that is 25 student if it is there. In the worst case scenario, make it clear, the point is in the worst case scenario, what is the worst case scenario? All are getting, but all are having different grades. So in that case, 25 students are there. Out of them, in worst case scenario, how many can obtain A? 5. How many can obtain B? 5. This way we are approaching. Make it clear, if you are having doubt that it is also possible out of that 5, all the 5 having A only? Yes, that is possible, but that is not giving a situation of guaranteed occurrence of 5 times B. So in this situation, when we are considering that 5 student they have got A, 5 student they have got B, 5 student they have got C, this way total how many students we require to ensure that all have got 5 different grades, 5 same
25.
grade? 25. Now it is asking that at least 6 will receive the same grade. If it happens, look, 25 where 5 have got the same grade plus 1 if we apply, that means what the pigeonhole principle means k plus 1 objects. So that one it goes to where? Definitely within a certain hole where already some existing pigeons are there. So it will go in a pigeon, it will identify a grade which is already someone has got. So that means 25 plus 1 if we go this way, that is total number of student, if it becomes 26, then we can ensure that at least 6 will receive the same grade. So these ABC grades are kind of whole concepts we are having, and this number of students we are having pigeons. So it is asking that how many objects, that is k plus 1 number of objects, and we are getting that this way we can ensure that 26 is the answer of this problem. Number of
Sir, can
students
you
that
repeat
require
the
20.
25 plus 1 part?
Okay, 25 plus 1, why we mention? If the worst case scenario we are thinking, that is 5 students they are having different individual distinct grades, then this way we are saying that 5 cross 5 total 25 students. The scenario is that 5 out of them have got A, 5 out of them have got B, this way. So our intention is what? At least 6 will receive the same grade. So we have reached up to 5. So one more same grade is required. It can be A, it can be B, it can be C. That is having no effect. So that's why 25 plus 1, the extra pigeon by extra student, if we consider, that student must ensure one of the grade. Out of these 5 grade, definitely one of the grade that student will get. And that is ensuring what? Previously 5 were having same number of grade. Now one, either A by B by C by D by E F, that will go accordingly, and it will ensure that 6 student they will receive the same grade. That means the pigeon it will go where already some existing pigeons are there. That is the approach of pigeonhole principle. So if theoretically little bit confusions are there, so that's why in a different manner let's explain this problem so that it will be a help. So we are saying this way that wait a minute, this one, there is a concept of generalized pigeonhole principle present. Make the point clear that generalized pigeonhole principle is talking something what? Now it is saying n greater equals to k plus 1 objects are assigned to k place. Absolutely. K place how many object? K plus 1, more than k plus 1 objects. So if it goes into k place, it is quite clear that one of the place must be there where that extra 1 bar 2 bar 3, because it is greater than mentioned, that will go. So that's why it is saying that one of the pigeonhole must have is symbol we know, that is floor of n by k. So floor of n by k, it is ensuring one thing, that is more than one object must be present in one of the pigeonhole. Actually, if k places are there, if we put k number of objects in k places, so we can expect that in worst case scenario every place, but best case scenario every place having one object. Now extra one object if it comes, where it go? In one of the existing place where already someone is there. So that means what it will be the count that time? It is 2. So more than 1 means more than 2 kind of scenario. So that is floor of n by k is the approach of pigeonhole principle. So let's apply this problem with this statement. N equals to 280 students in the class. There are k equals to 52 weeks in the year. problem is at least 1 week during which the birthday it will be same. Birthday it will be same. So week wise birthday we are talking about. So if k equals to 52 students are there, at least 1 week during which 280 n by k, n is 280 and k is 52. So 280 by 52 it's floor value. So floor value is coming 6. 6 students in the class have a birthday within a certain week. It is ensuring that that is uh, that must happen, except that any other situation is quite possible, but that is ensured one. So that is the approach of generalized pigeonhole principle. Like same type of approach if we ask with this way, 280 students are there, what is the largest value of n which we can prove that at least n student must have been born in the same month. So make the question clear first. We are having total 12 months in a year. Now, in the worst case scenario, if it happens that I am having 12 students whose birth month is different, birth month is different. So 12 students birth month is different. Then 13th student, if it comes, what will happen? One of the birth month it has to be common. Now that is the concept of pigeonhole. Pigeon will go into a hole where some already pigeon is there. Some pigeon is already there, kind of scenario. So this way, n by k we are dividing and its floor value we are choosing. So we are getting that 24 is the probable number of students whose birth month it is same. This way. So this is the pigeonhole principle. Now this principle we can use during the time of counting technique, but thing is that how to identify or understand that we will not apply permutation here or we will not apply combination here, but we have to apply pigeonhole principle here. So any suggestion from your side that this is a problem, I will not apply permutation, I have to apply pigeonhole principle. Which point by which one is saying that thing?
Again.
Which one?
This example.
This one. Okay.
Yes, sir.
So the example is saying that what is the largest pen for which we can prove that at least n student must have been born in the same month out of this 280. Now think with respect to number of month present in a year, that is 12. In the worst case scenario, if it is best case, worst case, make it clear what is that concept of worst case, best case. So in the best case scenario, it may happen you are having 3 students and they are having a birth month January, quite possible. But in the worst case scenario, what is possible? All the individual students birth month is different, so every month count is 1. So it is asking that at least n number of student birth month must be same. Now if I consider that 13th number of student in that worst case scenario, what is the worst case? Every student birth month is different. Now if 13th student come, what will be the situation? That student must have a birth month which already someone is having out of this 12. So that means if from 12 to 13 we move, from 12 student to 13 student we move, in the worst case scenario, it is ensuring that 2 students must have same birth month. My point is clear?
Yes, sir.
12 to 13 if we move, it is ensuring that 2 students must have same birth month. It can be January, it can be December, it can be May, anyone, but it is ensured that 2 students birth month is
same.
Are you getting this point? So this way, we are saying that the n by k 280 divided by 12, if we divide, then the ceiling value of 23.3, that is 24, it is ensuring that all of these 24 corresponding birth month, it will be same, because we are putting them where? Within the same pigeon hole. Which one? Now where the birth month is, say, May, but birth month is anyone out of these 12, anyone. So that's why n by k and its floor value we are getting. Actually, this is nothing but what? This is nothing but n by k plus 1. Make it clear. Once we are saying floor value, this is n by k integer value plus 1. So this is the n by k plus 1 kind of actual.
Okay.
So this way, we are having this technique, Pigeon hole principle. Then I'm moving to approach, that is this permutation with repetitions. I hope you can remember that permutation means NPR. NPR equals to n factorial divided by n minus r factorial. Out of the n element, we have to select r elements in ordered manner. That is the thing. Now, permutation with repetition, the formula is saying n to the power r. Fine. Uh, can you suggest why it comes like n to the power r? Make it clear. It is mentioned that repetitions. That means n object, every time I can select. Say first time I am selecting one object out of n object. What will happen in the second object? How many times, how many options I am having to select the second object? Again, n
N1.
times, because repetition is there. So my approach is going this way, that n first time, next time, again n, and whether these two situations are dependent, absolutely, because once you select the first element, then only you can select the second element. That means your second element is dependent on first element. This full product is required. So that's why it is going on this way, n into n into n into how many times? Now you have to select r number of elements. So that's why n to the power r. So permutation with repetition is n to the power r. Now, if permutation with repetition is n to the power r, then we also have this approach. Now make it clear, this is also permutation. This time, what is the difference we are having? It is mentioned that n1 non-distinguishable object, n2 non-distinguishable object, nk non-distinguishable object. So what is non-distinguishable object? If I consider that out of 100 balloons, 10 balloons, 10 red balloons are there, 20 yellow balloons are there, 30 blue balloons are there. So this way, N1, N2, Nk, we are saying distinguishable object. That means individually they are non-distinguishable. But with respect to N1 and N2, whether they are
Okay.
distinguishable, answer is yes. N1 and N2, they
Yes.
are distinguishable. But within N1, they are non-distinguishable. So repetition concept is present. Absolutely. How many times red balls are there? N1 times. How many
N1
times
times.
yellow balls are there? N2 times. So these are
N2
repetition. Repetition of individual non-distinguishable objects. So in this case, permutation formula is n factorial divided by individual repetitions we are having. Right? So this is non-distinguishable object corresponding one approach we are having. Again, in case of combination, we are having repetition concept. So combination NCR, we know that n factorial divided by r factorial into n minus r factorial. So in case of combination with repetition, our approach is n plus r minus 1 r. So combination, as we know, these are unordered element, unordered element. So in case of combination, it is saying that out of n elements, r element if you have to select, actually the selection becomes like this, n plus r minus 1 r. If you ask me why this way, so clarifications are required. So a standard book will help you. But right now we are interested about calculating in case of repetitions. So that's why I'm going directly with an example, or to an example, which will help me to identify how to identify that which approach is applicable and where and how we can apply that one. So finally, these approaches, whatever we have learned, means that's a gist. We can say that permutation n factorial by n minus r factorial, r combination n factorial by r factorial into n minus r factorial, we know this. These two repetition corresponding thing, permutation n to the power r, where all these elements are non-distinguishable. But once I'm coming r combinations, again repetition corresponding, this is n plus r minus 1 c r. So this way, we are having these formulas. So let's apply these formulas one by one. So I'm moving to the next one. Fine. So let's go with this one. Is it visible to all? I've changed that previous screen to this screen. Are you getting these slides clearly?
Almost.
Counting problem with repetitions?
Yes.
No.
That means whether I have to share it separately. Okay. Most probably right now it is visible to all of you.
Yes, yes.
Okay. Now, quickly we'll go through these problem statements. Okay. So make it clear that these are quite clear to all of us. Fine. So I'm saying that we are having this question, and these are the questions based on only repetitions. So our intention is what? Identify whether repetition kind of situation is there or not. If it is, then what type of repetition it is talking about. That means permutation corresponding repetition, a combination corresponding repetition. Fine. So let's go with the problem. How many solutions does the equation x1 plus x2 plus x3 equals 20 have, where x1, x2, x3 are non-negative integers? Fine. So make it clear that this is the question. How many solutions of these problems are there? What type of problem this one is? That means a problem based on combination or repetition, combination or permutation. Any idea from your side?
Combination.
Combinations. Okay. So definitely you are having your own logic. So can you tell me that using which logic you are saying this is a problem based on combination?
Because
That means the
order
dependency.
is not a matter. Does not
Absolutely.
matter.
Absolutely. So either x2 I am giving first, or x1 I am considering third. That's why ordered is not important. That's why combination. Absolutely correct. So this is a problem based on combination. Now, the same problem, once we identify that it is based on combination, if we say this way, that we have to select, in another way we are saying, we have to select this uh, 20. What is 20? Now 20 we are considering number of chocolates. Fine. So we have to select these 20 chocolates out of these 3. Whether 3 is number of chocolate, it is saying no. 20 chocolates we have to select out of these 3 categories of chocolate. What is categories of chocolate? Now we are saying that x1 means Cadbury, x2 means Park, x3 means 5-star. So you have to count 20 chocolates from this uh, uh, 3 different categories. Fine. So this x1 is clearly not a number of chocolate, but number of Cadbury. This is a category of chocolate. Fine. So that's why this way it is saying that x1 type 1 chocolate, x2 type 2 chocolate, x3 type 3 chocolate. Now once we are selecting, I can select Park at first, then 5-star, then Cadbury. This way we can go. So that's why, as he mentioned already, it's a problem based on combination. So this is a problem based on combination, and where repetitions are allowed, absolutely. Because if you have to fulfill this 20, you have to repeat this category more than one repetition, absolutely coming. So repetition is coming. So this is a problem of combination with repetition. So this way we are identifying the problem. So how to solve this one? Let's go with the solution approach, because we know that combination with repetition corresponding formula we are having. So this problem, once we are solving, so order we don't have to follow, that's why combination, fine. Now these are the three different categories, and during the selection chocolates have to repeat. So that's why this problem finally is coming combination with repetition. So we know the formula, that is we have to select 20 chocolate, so that's why it is R equals to 20 out of these three categories of chocolate. So that's why N equals to 3. So we have to select 20 out of 3. So that's why repetition concept is very much required. So formula is coming in plus R minus 1 R. So this way we are getting that this is coming C 20 to 20, and final answer 231 we are getting. Fine. So 231 is number of solutions of this equation. Are you getting the point? Whether is point is clear how we are solving?
Yes.
Yes, sir.
Yes.
Any question is there from your side?
Understood.
So first we have identified, is it for combinations or permutation, and then repetition is there, and then accordingly we have solved. So I'm just showing that running out of time, 10 more minutes are there from Zoom. So that's why quickly I must wrap up these things. Now same problem, but in a different approach. How many solutions does the equations have? But this portion is extra, where we have having some condition: x1 less than 7, x2 less than 8, and x3 less than 9. Fine. So I hope with respect to the chocolate example, now we can relate this condition. Actually, this condition is saying what? X1 less than 7 means what? X1 means we mentioned Cadbury. So this is what?
6.
Absolutely 6. Within this 20, maximum 6 Cadburys are allowed. Similarly, within this 20 chocolates, maximum
7
seven parts are allowed. So this way we can identify the significance of these conditions. Now whether repetitions are allowed, but
Yes.
repetition is required.
Yes.
Yes, because you are mentioning 6 times Cadbury, so that is repetition of Cadbury. So it's a combination with repetition kind of scenario we are having, but this problem we are solving in a different manner. Make it clear, the point is clear to us. So I'm just mentioning that what is the significance of these conditions, actually these conditions. So it is saying that, as you have noticed, that 6 maximum, 7 maximum, and 8 maximum, say 5 stars are allowed this way. So if the problem is clear, let go with the solution approach. So the solution is saying that max, I've chosen a function, and accordingly we have mentioned that one. Fine. So during the selections, we have to repeat these categories. So it's a repetition kind of thing we are having. Now, make the point clear how we are solving. First, we are assuming the reverse condition. It was mentioned that x1 less than 7 is allowed, but we are choosing a condition where x1 greater equal to 7.
Sir, sir,
Yes.
uh, sir, if x1 maximum is 6, x2 maximum is 7, x3 maximum is 8, then if all are maximum at the same time, then it will exceed 20.
Absolutely. So that situation is not possible. So that's
Not
why
Yes.
we are having, exactly, you have pointed out the correct thing, that some situations will consider and some situation will discard,
neglect.
and that's why we are approaching this way. Can you remember in which approach we apply this technique? Some situation we have to consider, some situation we have to discard.
No.
Okay, so that is principle of inclusion
Inclusion and
and
Inclusion,
exclusion.
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 Absolutely. So that's why some situations are allowed, some situations are not allowed. So that's why this problem, actually our intention is to solve using that approach. So that is a counting technique but different manner. That's why you are explaining. So let's go
Okay.
with that one. So if we have assumed the following condition, that C1, C2, C3 this way, next, what is NC1? Look, we are habituated to use combination with repetitions without any condition. N, C, C n minus r plus 1, comma r. That's formula, it not require any condition. But we are having this condition. So somehow we have to remove this condition and we will apply that combination with repetition formula. That is our intention here. Fine. And that's why we are considering this condition in a reverse manner. So once we mention NC1, what is that? NC1 is number of how many ways, ignoring the first condition, we can choose number of chocolates, ignoring the first condition. What is the first condition? Now x greater than equals 7. So this 7 we are discarding from both sides. This 7 we are discarding from both sides. 20 minus 7 and x1 minus 7. So x1 minus 7, if we discard this way, actually it means we are removing this condition from the equation. X1 minus 7, if we put here, it means we are removing this condition from the equation. So our equation is becoming x1 plus x2. That is the new x1. Actually, this is not x1, x1 dash, a new x1, where no condition of this kind of thing is there. So that is a new x1 plus x2 plus x3 equals to 20 minus 7, that is 30. How many way I can select 13 chocolates out of these three categories where no condition is given, but no condition we want to maintain. That means it's a combination with repetition problem, and that's why the approach is coming. We know the formula, and this way we are having the count 105. So please make this line clear, then only rest of the thing automatically it will be clear to us. Is it clear to all of us? N of C1 concept.
Sir, if we are removing x1 equal to 7 from both sides, then why we are adding
Absolutely.
x1 again?
Actually this is not x1, it should be x1 dash, a new version of x1 where no condition is applicable. Is
Okay.
that should be x1 dash, a new x1 actually, where no condition of x1 is there, and x2
Sir,
obviously not there, x3 not there.
sir, here x dash value is 0.
X1 dash value is, we
0.
can start from 0. Look, something we have written here, non-negative integer. So all these values starts from 0 up to this 20,
20.
because it can happen 20 plus 0 plus 0. Similarly 0
Yeah.
plus 20 plus 0, isn't it? So this way here it is coming that once I have subtracted 7 from this x1, it is becoming x1 dash. So this can starts from 0, 0 to 13, 0 to 13, 0 to 13. This way it is going. So n of C1, if we have counted the same manner, I have calculated nC2, that is ignore C2 condition from both sides and calculate the repetition. Similarly, ignore C3 condition from both sides and calculate the number of ways we can select that chocolate. So these are the one individual count. So that's why inclusion and exclusion, if you remember, afterward